control. Can that exist in an algorithm? It absolutely can. What I do for those ones, this one doesn't have control because it doesn't have a branch. But a control is kind of like a little wall. We don't want things to go past it. So I draw it at the end of them. If there was a branch command that was mattered on this one, I just draw a line at the end of the command, which means there's a little wall here. Now that doesn't mean I can't necessarily pull something across, but I have to be able to invalidate it if I do. And I can make something go after it, but I got to make sure it actually finishes then. Does that make sense? So that's my convention for these ones. That it'll be a line after the node that goes on. You just know everything to the left should stay to the left, everything to the right should stay to the right. And if you're going to move them, you better have a darn good reason why. Make sense? All right. So now we can take any sequence like this and we can look at it and we can say, how long will this one take to complete? What's the best time I can finish it in? 12. Can a pipeline machine achieve that? A regular original pipeline? No. All right? Can a Tomasulo's machine achieve it? Yes. All right? So you can start looking through each one of these and seeing what are examples that go in. Now, did I need the names? Can you still tell me whether or not a Tomasulo's machine could achieve this? Yeah, because it didn't matter on the names, did it? The only thing we needed the names for was how long did it take to finish, and that lets you map it back to code. So realize when I'm trying to build test cases or problems, I draw them up just as graphs. That goes on. And then I go, oh, okay, I need it to be this long to illustrate it. So what's it going to have to be? Well, this is going to have to be some short thing like an AOU operation. This is about 4 cycles. So I either better have something like a branch that fails or a memory operation. Right? So I can walk through and just pick intelligent cases for them and just generate problems. You guys are building a Tomasulo's machine. You want to test something? You should probably test to see, does it handle the problems that we said it handles? So do I just throw random code at it? Keep writing code until I'm blue in the face? I should probably just draw up a grid graph, find out what will cause, what should Tomasulo's handle, right, the good cases. Remember, when you do tests, what should it do? Test that. What should it not do? Where are the problems or the failures? Test those. That goes on. And then test a few random things. So if you follow that general scheme, you'll do fairly well. When we go into here, I can look at this and say, hey, you know, Tomasulo should handle this. So let me pick some code sequences that'll do that. Check it on my machine, see if it works. Tomasulo's could run into a problem with branches. So I should probably test a loop to make sure that it stops things and doesn't just keep running. Right? So this lets you know at the point now you can actually generate your own test codes. Draw the graphs to generate the problems, and then convert them. Right? Once you've drawn the situation that you need, you can convert them back, pick an instruction that'll have that dependence. You pick the instruction type for the length, and the data flow to match the arrows. And that's it. Good? Okay, we are at our time. So if there's no other questions, we got that. We'll move on next time, I think, is loop unrolling. This is kind of some software techniques of how we can handle some of these. All right, oh, I'd rather big blank from the end.